Good afternoon, everyone. I'm very pleased to be here to present part of my research. This research is for the time when I was a postdoctoral fellow with the Acceleration Consortium at the University of Toronto. I'm currently a concrete materials specialist at Arup, and I'm very grateful for this opportunity to be here and present my previous research. So today I'm going to talk about carbonation in concrete. So we're going to understand what is carbonation and why is it important, and what are the objectives of this research. And then I will move on to the modeling part of the research and the results that we got, and finally wrapping up with some concluding remarks. So carbonation is a physicochemical process in concrete where the CO2 molecules react with cement hydration products. And it's a very important durability mechanism in concrete. And if we want to look at the carbonation, we could say that usually carbonation can be studied from two perspectives. One is from the durability side, because carbonation can initiate the corrosion of a steel reinforcement in the concrete. But also we can study carbonation from the angle of sustainability, especially nowadays that we are counting on natural carbonation in concrete to absorb CO2 during its life cycle, and it's reflected in lots of roadmaps and action plans to reach carbon neutrality. So the part of this research is actually to model carbonation in concrete with AI-based models, and the results of this research could be used for any of these purposes listed here. So the objectives of this research was to collect two relatively large data sets, one on the accelerated carbonation and the other one on the natural carbonation. And the goal was to collect data sets that are matching with the same input features. And then we could predict the natural and accelerated carbonation depths in concrete. So we are trying to see the carbonation in low carbon concrete incorporating different types of SCMs. And also we are trying to use a probabilistic approach so we can quantify the uncertainty in the predictions that we are making, because basically carbonation is a very complex problem that is influenced by lots of different parameters, so knowing the uncertainty in the predictions is quite important. Then we also want to do a large series of numerical simulations and sensitivity analysis to find out if the model is able to capture the synergistic effects of different types of mix design and environmental parameters on the carbonation process. And at the end, we want to see how the accelerated and natural carbonation depths are correlated to each other. So the first step was to do a round of literature review to see what type of parameters influence the carbonation in concrete. So if we want to classify those parameters into three main groups, the first group is the material characteristics and mixture design. Basically the binder type and the binder composition, different types of SCMs, their reactivity and their chemical compositions, water to binder ratios, other mixed constituents, perhaps chemical admixtures or fine and coarse aggregates contents. And these parameters could have different level of influence on the carbonation process in concrete. The second sort of influential parameters are the environmental exposure, especially in terms of natural carbonation. So the ambient temperature, ambient relative humidity, atmospheric CO2 concentration, exposure type, carbonation time. These are the influential parameters that affect carbonation in concrete. And also maybe some engineering properties of concrete, compressive strength, porous structure, degree of hydration. And the goal is to find the carbonation front in the concrete or the carbonation depths, both accelerated and natural, in two different data sets. So here are the mix design parameters that we try to include in the data set. So the cement content, 5 different types of SCMs, GGBFS, fly ash, limestone, metakaolin, and silica fume, the water content, the aggregate contents, the chemical admixtures, and also the curing time and the curing regime in the mixtures. We also try to include the 4 main oxides of the cement and other SCMs that we used in the concrete mixtures. Here is for OPC, fly ash, and GGBFS, the silica, aluminum, iron, and calcium oxide contents, and also for limestone, metakaolin, and silica fume. Also, the natural carbonation is very important to look at the environmental parameters. So accelerated CO2 concentration, the ambient CO2 concentration is one of the most important ones. We also try to see the variation of temperature and relative humidity during 1 year of exposure. So we try to include 3 types of parameters for the relative humidity, which is the mean value, the minimum, and the maximum values. The same thing for temperature. So the average annual average value, the average temperature, the minimum temperature, and the maximum temperature. Exposure time and exposure type. So in terms of natural carbonation, exposure types could be, as you can see here, sheltered, unsheltered, and indoor exposure. And then for the accelerated carbonation, we only have the mean values of the CO2 concentration, relative humidity, temperature, and the exposure time, of course. So here's an overview of the collected data set. So if we look here, we took the natural carbonation data from published studies in the literature, which were measured in 16 different countries around the world with different climatic conditions. And here is an overview of the distribution of chemical compositions of the cement and SCMs for the accelerated and natural carbonation data sets. So I'm going to stick with this color code from here in the next slides. So the blue is for the accelerated carbonation, and the pink or red color is correlated to the natural carbonation. We are actually exploring different ways to incorporate the chemical compositions of the binders. Because we have 6 different binders and we are considering 4 chemical oxides, it could be 24 input features only for the chemical oxides of the binders, which is relatively a high number for input features in machine learning models with the number of data points that we have available. So one option that we are exploring is using a chemistry-informed feature engineering, where we can convert the chemical oxides into some reactivity modulus, for example, silica modulus, alumina modulus, and the lime modulus. And then we can take an average over the binder system that we have, and actually, instead of using 24 different chemical oxides binder content, we could use 3 of them for the whole binder system that we have. And here we can actually reduce the dimensionality of the data set that we have. So here's a quick snapshot of the a statistical description of a data set that we use. This is for the accelerated carbonation. So perhaps there are lots of data here, which is kind of a little bit hard to digest at a glance. But I just want to show how is the distribution of the data that we have here. This is for the accelerated carbonation, and this is for the natural carbonation. So we have different input features, around 24 input features in general for each of the models. And this is the overall framework that we use to find the correlation between the accelerated and natural carbonation. So once we have our model and we can predict the carbonation depths with our model, then we can use the Fick's law to find the carbonation rates for both accelerated and natural carbonation model. And then we can find this correlation index, which is the ratio of natural to, or accelerated to natural carbonation rates. So we use a probabilistic neural network, which consists of two different networks. One network is to predict the mean values, and the other network is to predict the standard deviation. So in that case, we could actually quantify the uncertainty in the predictions that we are having. As usual for many or perhaps all of the machine learning models, we've done lots of fine-tuning to find the best architecture for our model. So you can see here we consider different types of architecture with 2 layers, hidden layers, 3 hidden layers, 4 hidden layers, and 5. And if we find out that perhaps 3 hidden layer is the best number, because more than that doesn't actually improve the accuracy, but just add complexity to the model. So we stick with the 3 kind of hidden layers, and we tuned other parameters for that architecture. Here I'm showing some of the results for the predictions for the accelerated model on the top and the natural carbonation model on the bottom. So we can see that for the testing set, we can get pretty much good accuracy with R squared nearly of 0.95. And here, again, those slides are a little bit heavy on results and perhaps a little bit hard to digest just looking at them. But I'm trying to show here is that the model is able to find the uncertainty in the predictions. So here we have 80% confidence interval, 95% and 99% confidence intervals. And we can see, depending on the type of SCM that we have, we could have different uncertainty in the predictions, which could be related to the source of the data or to the number of the data that we had. As you can see, for some cases like silica fume or limestone, we didn't have that much testing data. But for example, for slag and fly ash, we had more data points, which could actually increase the certainty or reduce the uncertainty in the predictions. These results are for the accelerated carbonation, and we have the same results for the natural carbonation. And again, you can see the uncertainty could quite vary across different types of SCMs that we have. We've done lots of sensitivity analysis to find out if the model can capture the synergistic effect of different parameters on the carbonation process. So for example, here we can see that we have different binder content, different water-to-binder ratio, and different, in the case of accelerated carbonation, different different carbon dioxide concentration. And we can see that for both OPC fly ash and OPC GGBFS binary blends, the model was able to capture the effect of, for example, replacement of cement with fly ash on the carbonation. As you can see, if we increase the level of replacement, the carbonation depth goes up, which is pretty much in good agreement with the findings in the literature. And you can see that we can capture this effect across different types of mixture design parameters. Here is kind of heat map graphs that show the interplay between different parameters. So here we have relative humidity, CO2 concentration, fly ash replacement level, water-to-binder ratio, and you can see that for different values, the model was able to capture those effects and could pretty much reliably and accurately predict the carbonation depths. These are the same results, but for the slag OPC binary blends. Again, the model had a good performance on capturing the effect of different parameters. For example, we see that if we compare the fly ash and slag, we can see that the carbonation depths in slag-based mixtures are lower compared to fly ash mixtures. And again, we could have the same type of results for the slag. We also here have the results for the natural carbonation depths. So I'm going to quickly pass these kind of slides because there are similar results. But the point here is to show that the model can capture the effects of different parameters. So for the natural carbonation, we actually explore different scenarios. We took the environmental parameters or the climatic condition parameters of two cities, Toronto and Vancouver, and we consider different types of exposure, indoor exposure, outdoor sheltered, and outdoor unsheltered. And again, this is the interplay between different mixed design parameters and the environmental parameters. And when we compare the results with the findings in the experimental work in the literature, we can see that the model did a very good job in differentiating between the, for example, outdoor or indoor exposure types. And we have the same type of results for the slag also. So now that we perform that sensitivity analysis and we are confident in the accurate predictions of the model, we can go to the next step, which is to find this correlation between the accelerated and natural carbonation depths. So with those carbonation depth predictions, we can use the Fick's law, as I told earlier, to find the carbonation rates, and then we can find the correlations. So in these graphs, we can see that if we divide different mixtures with the same binder content and the water to binder ratio, but with different SCM replacement level, we can find a relatively highly linear correlation between the accelerated carbonation depths, carbonation rate, which is on this vertical axis, and the natural carbonation depths with a pretty much high R squared, as you can see here. And we can find out the ratio for the accelerated to natural carbonation. As you can see, those numbers could change a lot based on the different parameters. For example, from the literature review, we can say that an accelerated carbon dioxide coefficient concentration of 1 to 3% gives us pretty much results close to natural carbonation, and the carbonation rates ratio should be in the same sort of numbers that we are seeing here. But for higher CO2 concentration, for example, 5 or 10%, we could see the ratio of accelerated to natural carbonation is much higher. And this shows that at those concentration levels, the accelerated carbonation is not very similar to the natural carbonation. So we can get these good kind of insights from the model on how to design accelerated carbonation depths, accelerated carbonation in general, if we want to evaluate the long-term performance of concrete against natural carbonation. So these are the results for the fly ash. We have the same results for the slag, again for two cities of Toronto and Vancouver. And again, we can establish very good linear correlation indexes and correlation in general for the mixtures between the accelerated and natural carbonation. And again, we could have the type of same results here for the case of slag concrete. So in summary, both accelerated and natural carbonation models were able to accurately and reliably predict the accelerated and natural carbonation depths, and they could capture the synergistic effects of different mixed design parameters and environmental condition parameters on the carbonation process. And with the results, we could actually establish a linear correlation between the accelerated and natural carbonation for different binary blended mixtures with fly ash and slag. Of course, the model has some limitations. For example, how we could input the reactivity of different SCMs. As I told here, we use a reactivity modulus. We could use the straight chemical compositions in the model as an input features, but we don't have that much information about the reactivity of the SCMs in the published literature, which is a limitation in terms of data that we have right now. And at the end, this model can be used to serve for different purposes, for durability purposes and for service life modeling based on the, for example, FIB codes or it can be used to quantify the carbon uptake of concrete with different SCM contents. At the end, I want to thank my previous supervisors, Dr. Damon Panesar and Dr. Elias Khalil at the University of Toronto. I also want to thank the Acceleration Consortium at the University of Toronto and also the Environment and Climate Change Canada for supporting my research. And as I said, I'm currently working in the ARUP, and I would also like to appreciate the support of my colleagues at the Specialist Technology Analytics and Research team at ARUP Canada. I would be happy to answer any questions that you might have, and thank you for your attention.